Welcome back, everyone. I am Rado, and this is HackConf 2021 online edition. I hope you had a good stretch because we have more quality talks coming your way. And our next speaker is Zhivko Petrov, who is a C++ software engineer in the field of perception robotics. Have you ever wondered how pathfinding is implemented in games? Or how to calculate the area of a complex shape by only using random numbers? Well, we will learn this from Zhivko and his sidekick Batman. Zhivko, spam the chat, take it away.
Hello everyone, I will be talking about Batman and the algorithms. Before I begin, let me show you something real quick. Pretty cool, right? Do you want to know what algorithm was used in order to demonstrate that concept? I will make sure we find out in the next couple of minutes. Stay tuned. So, I wanted to open my talk with a motivational quote. Something like, always be yourself, no matter what. Unless you can be Batman. Then always choose to be Batman. Sadly, I'm not him. My name is Zhivko Petrov, and I'm a civil engineer who's been working heavily with C++ in the past 6 years or so. Currently, I'm working as a perception robotics software engineer for a company called Ocado Technology here in Sofia. If you want to know why we're so cool, don't be hesitant and ping me on LinkedIn. I will provide details after the lecture. So, have you ever been in a situation where a relative of yours asks you, hey, you're in IT, can you fix my computer? I hate that question. So something similar happened to me not so long ago. A friend of my father's approached me and said, hey Zhivko, you're a civil engineer, right? I want to build myself a pool. Will you help me? So, yeah, of course, I want to help you, but what? A pool? Yes, that's right, a swimming pool. I want to build one in the backyard of my house. It should look something like this. So, I helped the man with what I could. I found a designer who did the project, and I then asked him the most strange question of all times. Hey man, could you tell me how many square meters of darker blue tiles I should buy? Apparently, he was one of those people who loves advanced mathematics. So, to the answer of the question of how much square meters of tiles I should buy, I got this. Are you sure, man? Absolutely, I've double checked. This is the number. Okay, I trust you. So, I went to the nearest construction store and I told the cashier, hey, I want to buy this much tiles. Apparently, it did not turn out so well. But what could have I used? For example, I could have used some dedicated software like MATLAB in order to solve the integral. But imagine a situation where you can't use MATLAB because of some unexpected reason. For example, the Monte is suddenly unreachable and you have nowhere to get MATLAB from. We have to try something else. Using an approximation is another approach, which happens to be the very definition of how we solve integrals. So we take our integral and we start by dividing it into easy to calculate shapes. We divide the area by 2, make it two triangles, and you divide it again and again and again and continue doing so until you're satisfied with the result. But there is one problem in this approach. Computation aside, we actually do need additional linear space in order to store all of those shapes. This doesn't seem right. There has to be a better alternative. Think about this. Given the same integral, instead we do something else. We first find the bounding box rectangle. So we find the maximum y, maximum x, and say, hey, this is our bounding box rectangle. Next, we will use random points. That's right, random points. We generate the first random point and check if that point is inside the integral or not. For example, this point is inside the integral. Good for us. We generate another random point, which happens to be outside the integral. And we continue doing so again and again and again until we have enough data, enough samples. And what to do with that data? We find the ratio between the inside points versus the total number of points. Multiply that by the bounding box rectangle, and voila, you have the integral area, or at least a very, very close approximation to that area. And the beauty of it is that we actually do need no additional space, or only for two integers, the two counters we're keeping track of, which is very cool. This algorithm is called Monte Carlo, or to be more precise, it is Monte Carlo integration. It has its name originating from the famous gambling destination, the city of Monte Carlo. And you may ask yourself, why gambling? Because, as we said earlier, we are using random points to generate our input data. So now we have a mission to choose a random number generator. Sadly, in computer science, there are no pure random number generators. Instead, we use pseudo random number generators, short for PRNG. So I am choosing the famous Mersenne twister PRNG. And something important, you have to pick a PRNG with a relatively large scale. If you take pay close attention here, you can see that the period of the Mersenne twister is indeed huge. And if you don't know what a period is, this is the number of samples after which the generator will start repeating itself. So we need big number of samples, otherwise we will bias our data. And something else, our data that we are generating should also be uniformly distributed. And you may ask yourself, why? Because if it's not uniformly distributed, we will get this phenomenon which is called density of samples, which will corrupt our calculations. It will make them invalid because we have a bias towards certain area of our bounding box. Now combine all of this and we need a way to actually measure how our algorithm is behaving. We need to temporarily use an alternative method for finding the integral area and compare it to our algorithm performance. Something interesting with this chart is the more samples you feed your Monte Carlo with, the better the result. But this is true only to a certain threshold. Above that threshold, the algorithm performance will start to vary by a tiny fraction. So we're not interested in that tiny fraction because it is giving us a good enough approximation to the actual result. But alright, enough theory. What should we do with this new knowledge we've just acquired? For example, we could integrate over those set of equations, which, if we represent, happens to be the Batman symbol. Demo time. So I'm going to run the same demo as I did in the beginning of the talk, but this time I will show you the texts behind it. I'm going to integrate over 2 million points, and let's examine what happens. Pay close attention to the error at the bottom left of the screen, 0.01%. Let me rerun the same program. Its outcome will probably be different. Why? Because the input is random. The output is also random. But we're interested that it is giving us a good enough approximation to the actual answer, which is what we're looking for after all. But if I change something, if I, for example, reduce the number of samples from 2 million to 20,000, let's see what happens. I get a bigger error, and this is to be expected. But something interesting, not only is the error bigger, we also have a smaller computation time, only 30 milliseconds as opposed to around 4,000 milliseconds in the previous example. So what do we learn from this? The more samples you feed your Monte Carlo with, the better the result. But it will take you more computational time, which could be applied somewhere else. It is all about balance. Okay, I've got another one for you. In one of my previous employers, me and my colleagues were given a task to implement a Batman minigame. So it involved features like real-time pathfinding, which was needed to achieve different features. So I said to myself, okay, Zhivko, you can do this. Use your C++ knowledge. It would probably take you around a week or so to finish the implementation. And then something unexpected happened. Let's say 30 minutes later, one of my colleagues told me, I'm done. You what? Yeah, man, I just used Python. I found this library online, which someone already implemented, so I just imported it, and that was all. And I was shocked. I mean, literally shocked. I needed to test this, and so I did. I've benchmarked the Python version, and something interesting happened. While testing, the CPU cooling started howling like a wolf on its mating season. Apparently, Python was not the best tool for this job. Of course, I'm over-exaggerating, but you get my point. And then I said to myself, okay, Zhivko, you got this. Use your C++ knowledge, use your data structure knowledge, use your algorithm knowledge, and make it shine. All I need to do is probably some graph theory plus pathfinding. But the question is how to properly implement it, how to find the shortest path from point A to point B in our application. The same question, for example, Google has to answer when we go from Sofia to Burgas. It finds the shortest path. But how is the application able to find it? I know it is probably using Dexter. After all, it is one of the most famous algorithms for calculating the shortest path. Let's check what Dexter is. Given a weighted graph with some nodes, we have a start node A and a destination node E, and we want to find the shortest distance from the start to the end. And the numbers is the cost. In this case, it's the distance between the different cities. So we represent all the nodes, and we're going to be storing them in a data structure. The data structure that uses the best implementation is a heap data structure, which always keeps the element with the biggest priority on top. So we start by adding the first node A. It has a current cost of 0 because we are currently located at the start node. Then we update, we add its neighbors by popping A, and we add the next nodes B and the next neighbor, which is C. The costs are now updated from the start node A. Next thing we want to do is pop the node to rearrange the nodes, so the node with the biggest priority, the lowest number in this case, will get on top. Next, we want to process that node. We pop the node, but when we're doing so, the neighbors of that node has to be updated as well. So the node B has its cost updated. It previously had a cost of 3, but now it has a cost of 2 from A to B. And the same thing we do for the other neighbors if we have them in the data structure as well. So E was the other neighbor of C, which we add to the equation. Next, we rearrange, pop the node B and add its neighbors. we get D added into the heap, nodes are rearranged, and then the same principle is applied. The cost of E gets updated from 9 to 5, and voila, we've just found the shortest path from the start node A to the destination node E. But in order to do so, Dexter had to expand all of the nodes in the graph. Okay, returning to our examples. Is actually Google using Dexter? Probably Sofia Burgas is a very famous destination and they do some fancy optimization. Let's try something not so convenient. For example, destination between Apriuti and Kukice. And they do it again. They find the shortest distance and even give us an alternative routes. But we spot something interesting. If I zoom in on the Apriuti region, I will see that there are not only big roads, there are also a lot of smaller roads in our national infrastructure. And Dijkstra had to expand all of those nodes. That sounds like a lot of computation. Ouch. Even more, it has another pitfall that if the start node S is located, for example, in the middle and we want to go to the end node, Dijkstra will prefer expanding nodes with lesser cost to the left, neglecting that we are actually getting further away from the end node. Even though Dijkstra is very practical algorithm, it surely has its pitfalls. And then I found something interesting on the internet. I've read about this optimization on Dijkstra called Astar. It basically was Dijkstra plus the ability to guide its behavior. Are we going in the right direction or not? Whoa, I should definitely try some of that. And then suddenly my research time was over. I was pulled by my manager, Gary. Yes, this is Gary on the right. So he told me, Zhivko, enough, we needed ASAP. Just use Dijkstra. No, Gary, I just read about this awesome Astar. I want to use that algorithm. Zhivko, we don't have time. Just use the Dijkstra. It will work. Gary, I insist. I want to use the Astar. I know I can do it. So stubborn as I was, Astar it was. Demo time. So now we have a 2D grid map with some start node, with some end node, and those in the middle are obstacles. So the A-star algorithm is able to guide the direction of the nodes who are expanding. Are we going in the right direction or not? So Batman is able to find its way from the start to the finish. If I change that, for example, I want to allow diagonal movements as well, go from here to here, let's see what happens. I'm able to change the behavior of the algorithm, how the shortest path is calculated in runtime, so I can modify the algorithm behavior. And if I forbid diagonal movements again, let's see what happens. Again, the algorithm will find the shortest path, but it will do so with the function you're telling it to calculate. Is it going further away to the target or not? And if I spice things a little bit, let me choose another level, and I want to go from here to here and add some runtime obstacles to make it a little more harder for the algorithm in order to check if it will be able to find its path. Let's see. And it seems that the algorithm does it again. That's pretty cool. I'm feeling confident and I'm proud of what I have built. Okay, but what if the path is actually blocked? What if we don't have a possible solution from the start node to the end node? Then the algorithm will also handle it. It will say, I cannot find a shortest path. So cool. I'm feeling really confident I'm returning to Gary, and I tell him, Gary, I'm done with the implementation. Well done, Zhivko. Good job. But to be honest, I've benchmarked it, and it was actually slower than the Dexter. Ah, never mind. Ship it. We just need it now. But you have to put up some extra work for the time you've lost. Woohoo! Wait, what? So yeah, I've shipped it like Gary asked me, and then I made a research. I made a research on what I did wrong. I've compared the both algorithms on paper and tried to find what went wrong. So the Dijkstra algorithm uses a cost function in order to evaluate where to go next. This is the cost from the current node to the next node, while the Astar uses that same cost but adds an additional function which is called heuristic function. This function is an approximation from the current node to the end node. We're using that heuristics in order to guide the algorithm, is it going in the right direction or not. Dijkstra is guaranteed to find the shortest path, while Astar is guaranteed to find an optimal path, not the shortest path, if your heuristic is admissible, meaning it would never overestimate its actual cost. But here comes the interesting part. The Dijkstra will expand all the nodes, while the Astar will expand the nodes that only seems promising. This is the real benefit. I mean, I don't get it. Clearly, the Astar is a winner here. What did I do wrong? Interesting. Astar also has some pitfalls. Let's examine those. The algorithm does not behave so well if we have special features like teleports or portals. We also need knowledge about the end node, about our target location, in order to apply heuristic. And the algorithm behaves poorly if the heuristic function is bad. Aha! I knew it. I was not an idiot. It's just that my heuristic was bad, which is more or less the same thing, but that's a topic for another time. Moving on. What is actually the Astar algorithm? Let's take a sneak peek. We have some graph again, and we want to go from the start node S to the end node E in an optimal distance. We need to do it fast. Again, the algorithm uses actual cost, which are the black numbers, and it is the same as in the Dexter example. But now we're adding heuristic function, which are the green numbers. In this example, I've chosen the heuristic for air distance. So the distance between J and A is 3, the air distance between D and E is 6, and so on. And the algorithm computes a total score when we combined the two costs. The principle is the same, the data structure is the same, it's a heap. We add the first node S, add all of its neighbors, A, B, C, and D, and for example, if you take D, it has an actual cost of 2, which is this number, and a total cost of 8, which is 2 plus 6. Then we pop the node S and rearrange the nodes in order for the node with the biggest priority to get on top, and we add its neighbors, the same thing we did with Dexter. So the next nodes are K and J, and for example, K has a cost of 7. Why? 2 plus, K has a total cost of 13. 2 plus 4, 6 plus the heuristic 7, it is 13. So we pop D, rearrange the nodes, and we have the node J. We pop J and update its neighbors if they're already in the data structure. Now pay close attention, we already have K in our data structure. We update its value. Why? Because we found a shorter path to K that has the value of 5, which that has the value of 4, which previously had the value of 5. And we add the next neighbor of J, E, which is the node we are looking for. We rearrange the nodes, our target node is on top, and boom, we're done. what just happened? We found ourselves a solution, an 8. But wait a minute, this is not the shortest path. The shortest path is actually here, which is the number 7. But remember, A star does not find the best solution, it finds an optimal solution. But what did we just gain? We gained that we did not have to evaluate all of those nodes, and especially we did not have to evaluate all of those nodes to your left. Imagine a scenario when you have 20,000 nodes. This is huge. So okay, how to choose a good heuristic and not fail miserably like I did? You need to choose your heuristic depending on the allowed level of movement. If you only have horizontal and vertical movements in your grid, use Manhattan distance. If you have diagonal distance as well, in addition to your horizontal and vertical distances, use the diagonal distance heuristics. And if your character, for example, could turn in any direction, for example 22 degrees to the left, then choose the Euclidean distance heuristic. Okay, let's examine those quickly. The Manhattan distance heuristics is actually a stripped down version of the Pythagorean theorem. We find delta x, delta y, and multiply them by some constant d. But the question is, how to find the d? C++, an example C++ implementation which I'm showing you, I'm using the simple integer 10. Why 10? I will explain you in the next slide. For now, the important thing is actually that a very small percent of the nodes actually get expanded. We don't have to expand all of those gray nodes that are in our grid map. So huge performance win. Okay, but what if we could use diagonals as well? The pseudocode is more or less the same with a few minor modifications. We have a new constant d2, which is 14 in my example. I will explain you why in a second. And if we visualized it, it is behaving pretty good again. So okay, now why the integers 10 and 14? Because on a typical 2D grid map, all of the horizontal and vertical distances are actually the same. So we can, for example, say this distance is equal to 10. And if it's equal to 10, the diagonal will be what? 14.4. But I'm using 14 for two reasons. First, out of simplicity. Second, in order to stay in the integer range, to not go in the floating point kingdom. And now, last but not least, the Euclidean distance heuristics. It is actually using the Pythagorean theorem implementation involving square root and so on. And this heuristics is one of the most famous heuristics because it is easy to apply and it is giving you a lot of freedom that you can move in all directions. Sadly, if you run it on a 2D grid map, you won't get a satisfying result. Why? Because on a typical 2D grid map, you can move in 8 or 4 directions. You could not move like the 27 degrees east and so on. Okay, but there is something else. This is an important heuristic. We have to make it work somehow. It has a bottleneck that it uses the square root method. Have you heard of this quote? Avoid square root and power methods like the plague. Why? Because they're slow. Don't be one of those people who, when you have 2 points and you have to find are they closer to a third point, you just blindly invoke the square root and power methods. Just don't be one of those people. Instead, what you can do is compare their square distances. This way, you win both. You implement your function without paying the heavy price of invoking square root. Okay, let's apply that to our Euclidean heuristics and see what happens. Fingers crossed it will work. Oh, come on! What happened now? Our A star transformed into greedy best first search. And the reason for that is that the cost function and the heuristic function does not have the same scale. The heuristic function is squared while the cost function is not. This is driving the algorithm towards the end node using air distance, neglecting obstacles along the way. So the conclusion is do not use this. And now you will probably say, okay, Zhivko, a bit of mixed signals here. You're telling us don't use square root, but actually use square root. That's right. Remember, when using randomized and heuristics algorithms, we can alternate between speed or accuracy. If you want accuracy, use the mathematical square root. If you don't want accuracy, use something like fast square root approximation. For example, a typical C implementation, which originates back from the days of Quake 3 Arena, has a implementation like that. Of course, I'm not going to delve into details because that function involves some serious amounts of witchcraft inside it. Of course, if you're interested, there are like 20-minute long videos on YouTube that you could check. Okay, so we have the speed and we have our Euclidean distance fixed. Way to go. But there is something else. I've been talking about this thing called a tiebreaker. Because if we don't apply this optimization, even a normal Manhattan heuristics would look like this. Sadly, we said in the typical 2D grid map that actually a lot of the distances are the same. So if I take, if I take that example, this is the same length as that example, this is the same length as that example, and so on. There are many paths with the same length, so they will all be expanded and they will be treated equally. Instead, what we want to do is simply modify a little bit our heuristics. This will make nodes that previously had the same cost now be different. And the question is, should you modify the scale downwards or should you modify it upwards? If you modify it downwards, Astar will prefer expanding nodes closer to the start. And if you scale your heuristics upwards, it will prefer expanding nodes to the end. Probably you want to go with the latter. Final thoughts about modifying the heuristics. If we now apply the tiebreaker, everything is back on track, which is awesome. And even if we have obstacles along the way, A1 struggles for a bit, and the moment the obstacle is overcome, the performance is back on track. But modifying the heuristic is actually a band-aid fix for an underlying inefficiency in your algorithm. Why? If you find yourself in a situation where your game contains a lot of obstacles, maybe a 2D grid map is not the best choice. Then you have to think for something else, an alternative map representation, for example, like polygonal maps or even navigation meshes. If you think about it, now we have very few contact points that we could jump, and we could apply what heuristic? The Euclidean heuristics. The question that I've shamelessly skipped in the beginning was, why learn algorithms? Because I think they play a fundamental role in the growth of any software engineer, because they help us solve problems in our everyday life. For example, choosing the best data structure for a given problem, like improving our problem solving. And last but not least, algorithm expertise turns a good engineer into a great engineer. Hey Gary, about the extra work you've mentioned. Oh yeah, I almost forgot. I need you to Dockerize your application, write unit tests, and build a CI/CD pipeline for it. Oh. Thank you everyone. I hope you enjoyed it. I hope you learned something new. You can find the code for the demos I've showed you on my GitHub page, and I would be really grateful if you pinged me on LinkedIn and said hello. Now, I think we have some time left for a Q&A session. What would you like to know?
All right. All right. So imagine a full round of applause from a very big hall. This was really interesting. Thank you again for the presentation.
Thank you, Carlo.
We have a couple of questions coming, and the first one is, where did you learn algorithms?
Where did I learn algorithms?
Yeah.
So algorithms was a thing which I learned when I started coding in the beginning. So I just knew how to code, but I found some courses on the internet. I found some really cool demos, some really cool trainings here in Sofia, training hubs that trained applications. So my guide to everyone is learn them. You may not apply 100% of those knowledge right away, but it will pay off, and it will pay off big times. So use it.
Right. Okay, more questions. How can we decide what algorithm to implement for a certain scenario?
How can we decide what algorithm to implement? So given your scenario, for example, if you have to search for something, you need some steps, for example, how to evaluate your board or game or application, I don't know what you're referring to, compute some score for the different scenarios you're able to take, evaluate those scores and pick the best one. For example, those are called greedy algorithms, but there are more optimizations that could be applied to think several levels ahead. For example, those are in some implementations, in some games like chess, you could use minimap or alpha beta pruning on top of that, and so on.
Right. Next question. I usually don't read the names of the people asking, but I will read it this time because it's a good name. This question is coming from Tosho Wosho. Wouldn't scaling the heuristics downwards make it non-admissible?
Wouldn't scaling the heuristics downward make it less admissible? I think so, yes. But as I said, this is a band-aid fix. So yes, in theory, it would make it not admissible, but you're modifying it by a tiny fraction. The idea is to compute different numbers, for example, 2000 versus 199, so you can differentiate the different nodes.
Right. More questions. What kind of games have you implemented?
What kind of games have I implemented? Well, I've also only implemented games. I've only implemented games professionally for the casino industry, but I've personally implemented small 2D games as my hobby. So platformer is my best choice.
All right. And I suppose in the same field is the next question. If someone's interested in graphics, what would you recommend as materials, as learning path? Like building graphics, building games?
Very good question. So if you watch some tutorials, they will directly tell you, hey, go take some big gaming engine, for example, Unity, Unreal Engine, and so on. My advice is don't do this. Write a game engine yourself, a very simplistic one, a 2D game engine. This will give you the ability to understand what is happening, how to work with a graphical API. And when you're feeling confident enough, then switch to 3D APIs. Try to touch the low-level graphical libraries, for example, OpenGL, Vulkan, and so on. And then you can use the game engines I've told you. Otherwise, there's knowledge is not directly applicable to the next engine.
And where should one reach for knowledge for how to build this simplistic 2D game engine? Is it books? From your experience?
So from my experience, the best, it's a C library, which I'm most fond of. It is called SDL2. It's actually not a graphical library, but it's a cross-platform tool that is giving you audio, video, inputs, mouse, keyboards, and so on, and you can build abstraction over that one. Of course, there are C++ variants, for example, SFML, and so on, but those are 2D APIs. First, start with them.
All right. How do you remember the core principles of each algorithm? Because this is what I find as the hardest part in learning them.
So how do I remember the core features of each algorithm? Probably you have to associate them with a real-life example. This is why I'm trying to demonstrate real-life usages of those algorithms that you can map in your head. Don't go chase the actual implementation. If you make me now to write the Astar from scratch, probably I won't be able to do it without looking from somewhere. But you need to understand the concept and then find the information when you need it.
All right. Well, this is a very good answer. Understand the concept, the key things there, the actual implementation.
Mhm.
When you get to it, you'll figure it out. So those are all the questions that we had. Once again, thank you very much. It's really nice talk.
Thank
A
you,
lot of
Rado.
visual
Thank you, everyone.
examples.
It was a pleasure for me.
I suppose we will share it with Discord
Mhm.
for the examples and for everything else. And we will be back here at 6 p.m. So have a nice break.
Bye, guys.